In this video, we're going to look at how we can model radioactive decay. Radioactive decay is a bit like a coin flip. It's random. It could be heads or it could be tails. And we don't know what it's going to be. However, if we have enough coins, we can make predictions and we can use statistics to get an idea of the pattern. So what we're going to do is we're going to start with 50 coins. We're going to throw them, see how many turn up heads and tails, and then we're going to plot a graph of our results. So let's get started. So what I'm going to do, I'm now going to remove any that have heads. So I flipped them once and I removed 24 coins that have heads. So you'd expect it to be about half, but it's random, so it will never quite be half. So that means I've got 26 left. Let's flip them again and remove the heads for the second throw. This time I removed 11 heads, which means I've got 15 left. So again, you can see it's roughly half, but it's not quite half because it's random. Let's carry on until we get to 0. So as you can see, I completed the experiment and I got down to 0 coins at 10 throws. So what I'm going to do now is I'm going to plot a graph of my results. I'm going to start with 0 throws and I have 50 coins left. After 1 throw, I have 26 coins left, and I'll just quickly finish this graph. So I've got this graph here that looks like a nice curve. So what I'm going to do now is I'm going to plot a line of best fit that goes through this curve. Although we could also describe it as a curve of best fit. So I know it looks like I'm joining the points dot to dot, but I'm not, where it's here, where it's not quite as smooth. So now I've got a nice line of best fit. And what I can use this line for is to work out the half-life, the time it takes for half of the coins to turn up heads and be removed. So to do that, I'm going to start at 50. I'm going to halve it because then I'm removing half of my coins. And I'm going to go across and I'm going to go down and I'm going to see what my half-life is, and I can see my half-life equals 1 throw. And then if I do that again, if I start at 25 and I halve it to 12.5, we'll see that the next half-life, the time it takes to go from 1 to 2, is again approximately 1 throw. It's just over 1 throw. It's actually about 1.1. Okay, and here we can see again it's actually about 1.1 throw. And that might seem completely obvious because we're doing with coins where it's half each time, but we could do this with dice. We'd obviously get a slightly different result, but it would work, and the half-life would always be constant. We could do it with radioactive particles, and again we would see exactly the same thing, that the half-life is constant each time. Importantly, it doesn't matter how many coins I start with or how many radioactive particles I start with. If I start with 50, my half-life will be 1. If I start with 25, my half-life was 1. If I started with 1,000,000 coins, you'd still find out that that half-life is exactly the same, and that's the same as it is for radioactive particles.